In the last two modules, we have discussed sign test. We have seen that sign test is based on the signs of the observations. In this module, we shall provide another non-parametric test based on the sign and order of the observations. This test is popularly known as Wilcoxon Signed Rank test. We shall give the exact distribution, summary measures, and some related properties. We also provide the modification when there are several ties present in the dataset. We have already discussed sign test as a non-parametric competitor of students' t-test. Some properties, including small sample and large sample, are discussed. But sign test only uses the sign of the differences and hence utilizes only a partial information contained in the data. Now, we shall discuss another competitor of t-test, namely Wilcoxon Signed Rank test. This test was developed by Frank Wilcoxon in late 1945 but popularized by Sidney Siegel. As is evident from the name, it uses sign and rank of the data together. In fact, it assumes symmetry apart from continuity of the underlying population to provide a distribution-free procedure. We have already seen that the data can be non-normal in practice. If non-normal data comes with added feature of symmetry, sign test is no longer sensible. In such a case, Wilcoxon Signed Rank test is a valid alternative. For the development of Wilcoxon Signed Rank test, we need to define few basic things. Suppose x1, x2, xn are IID observations from a symmetric location family of distributions f. Then fx equal to fx minus theta, where theta is the location parameter. Now, it is also assumed that f is continuous and symmetric. Now, one can recall that symmetry implies a symmetric density and probability content above and below the point of symmetry are the same. Then, under symmetry, xi minus theta and theta minus xi have the same distribution for each I, and hence theta in this case is a median of f. Then, our objective is to provide a test for theta equal to theta naught against the usual one or two-sided alternatives. Since under h naught, xi minus theta naught has a distribution with median at 0, we can, without any loss of generality, assume theta naught as 0. Now, we further assume that probability xi equal to 0 for all I, and that the observations are distinct with probability 1. Suppose the observations are arranged in order of absolute value and ranked accordingly. Suppose Ri plus is a rank of modulus of xi among modulus of x1, modulus of x2 and up to modulus of xn. Signed rank of an observation is a rank of its absolute value multiplied by the sign of the original observation. If Zi denotes the indicator of xi greater than 0, then the signed rank of the ith observation is Zi multiplied by Ri plus for I from 1 to n. Wilcoxon Signed Rank test is based on the sum of the ranks of the positive observations. Then, formally, the signed rank sum T is defined as the sum of the signed ranks, that is, T equal to summation I from 1 to n Zi multiplied by Ri plus. It is often a matter of confusion that only positive observations are to be ranked. But this is not true. In the following example, we shall explain the difference. Consider the following data with n equal to 10 xi's are given. Now, for the observation with value minus 11, rank of the absolute value is 6, but contribution of this observation to T is 0. So, we are ranking both positive and negative values, but the contribution to T of the negative value is 0. Now, we shall explain the nature of T for varying theta. Suppose theta greater than 0. Then xi's are expected to be larger under theta greater than 0 than under theta equal to 0. Actually, most of the zi's are expected to be larger in such a case, that is when theta greater than 0. Thus, we get a large T in this case. Therefore, a large T is an indicator of a positive theta. Then, it seems reasonable to reject the null hypothesis against theta greater than 0 if T tend to be too large. In a similar fashion, the other alternatives can be explained. We have just seen that T can be used to judge whether the data supports theta equal to 0. But what is the guarantee that T will be distribution free under theta equal to 0? Now, we shall show that T is indeed distribution free under theta equal to 0. First, we introduce the concept of anti-rank or inverse rank. Suppose n observations are ranked from smallest to the largest. Then we get the vector of ranks as R1, R2 up to Rn, which is denoted by R vector. Now, D or the vector D is anti-rank if the composite vector R of D, that is R in the suffix D1, R in the suffix D2 up to R with suffix Dn is a vector 1, 2 up to small n. Let us consider an example. Suppose the rank vector is given by 3, 2, 4, 1 and 5. Then if D is the anti-rank, then R of D must be 1, 2, 3, 4, 5. Now we say that R4 is 1. Thus D1 equal to 4. Again R2 equal to 2. Indicates D2 must be 2 and so on. Thus D is a permutation of rank vector such that R of D is the set of positive integers ordered naturally. Now we shall express T in terms of the anti-rank vector D. Observe that T is the sum of few numbers from the set of first n integers and 0. We can arrange the ranks in such a way that the ith rank comes in the ith position. If D is the anti-rank vector corresponding to R plus vector, then in such an arrangement Zi becomes Z in the suffix Di. Thus we get T as summation I from 1 to n I multiplied by Z with suffix Di. Now we shall show that the vector Z1, Z2 up to Zn and the vector D1, D2, Dn are independently distributed under theta equal to 0. Under theta equal to 0, xi are iid fx, where fx plus f of minus x equal to 1 due to symmetry. Naturally, f has median at the origin. Then, for every x, we find the joint probability of zi equal to 1 and modulus of xi less than equal to x as half into twice fx minus 1, which is again nothing but probability zi equal to 1 multiplied by probability modulus of xi less than equal to x. Actually, zi are IID Bernoulli random variables with success probability half. Therefore, probability zi equal to 1 is half. And since xi has symmetric distribution, probability modulus of xi less than equal to small x comes as twice fx minus 1. Similarly, the joint probability of zi equal to 0 and modulus of xi less than equal to small x comes as probability zi equal to 0 multiplied by probability modulus of xi less than equal to small x for every x. Since zi and modulus of xj are independent for any I not equal to j, the desired independence follows. Now, being a function of modulus of xi, I from 1 to n, r plus is independent of zi. Thus, zi and di are independently distributed for I from 1 to n, as d vector, the vector of anti-ranks, is completely determined by r plus, the rank vector. Now, observe that zi are IID as Bernoulli half, as we have already noted, and we shall show that zdi are also IID Bernoulli half. Now, the is a random permutation over script P, the set of all n factorial permutations of 1 to up to n. Then, using a total probability law, the joint PMF of ZD1, ZD2 up to ZDn is seen to be half to the power n. Since half to the power n is the joint PMF of n IID Bernoulli half variables, the result follows. Thus, Z1, Z2, Zn and ZD1, ZD2, Zdn have the identical distribution under H0. Thus, T is the weighted sum of IID random variables with known weights, and the variables are Zdi I from 1 to n. Now, under the symmetry about the origin, Zdi are IID Bernoulli half variables. That is, the distribution is independent of any f. Hence, being a function of Zd1, Zd2 up to Zdn, the distribution of T is independent of any f. Thus, T is exactly distribution free under the null hypothesis. Therefore, tests based on T are exactly non-parametric. Now, we shall obtain the distribution of T under theta equal to 0. So, first of all, assume theta equal to 0 and consider the representation T equal to summation I from 1 to n I Zi, where Zi are IID Bernoulli half. This is possible as under theta equal to 0, Z and Zd vector have the same distribution. If all the observations are negative, T is 0, and for all positive observations, T is n into n plus 1 by 2. And for positive and negative mixed observations, T lie below 0 and n into n plus 1 by 2. Under theta equal to 0, each value of Zi are equally likely. And we have 2 to the power n such possible value of Z1, Z2, Zn. Thus, we have probability T equal to T equals B Tn divided by 2 to the power n for T running from 0 to n into n plus 1 by 2, where Btn is the number of n tuples Z1, Z2, Zn such that summation I from 1 to n Izi equal to T is satisfied. Although no closed form expression exists for the distribution of T, we can compute the distribution for smaller values of n using the above definition. First of all, we develop a recursion relation for Btn. We can calculate Btn using the relation Btn equal to Bt n-1 plus Bt minus n n-1, where Btn equal to 0 for T less than 0 or T exceeding n into n plus 1 by 2. Note that Zn, the last quantity of the tuple, is either 0 or 1. Then the recursion relation follows from the fact that Btn equal to number of Z1, Z2, Zn minus 1, that is n minus 1 tuple involving Z1, Z2, Zn minus 1, such that summation I from 1 to n minus 1 Izi equal to T minus n plus the number of Z1, Z2, Zn minus 1 such that I equal to 1 to n minus 1 Izi equal to T. Note that B0n equal to 1 for every n exceeding 1, as we have only one possibility, that is Zi equal to 0 for every I. Again, B1n equal to 1 for every n, as the single possibility is Z1 equal to 1 and Zi equal to 0 for I greater than equal to 2. Now, calculation of the distribution with small values of n will be helpful to understand the role of the recursion relation. Assume n equal to 2. Then n equal to n plus 1 by 2 is 3, and hence possible values of t are 0, 1, 2 and 3. Then B02 and B12 are both unity. Now, using the recursion relation, we get B22 equal to B21 plus B01. Now, B21 equal to 0, as getting 2 with n equal to 1 is impossible, but B01 equal to 1. Then we get B22 equal to 1. Again, applying the recursion relation, we get B32 equal to B31 plus B11. Again, B31 is 0, as getting 3 with n equal to 1 is not possible. However, B11 equals unity. Thus, B32 equal to 1. Hence, each value of t occurs with equal probability 1 by 4. Next, consider n equal to 3. Then, using the recursion, the distribution can be obtained. However, we skip the details. Now, if we look at the distribution of t, we see that the probability mass function increases to a maximum and then decreases. The maximum occurs at 3, that is, at the n into n plus 1 by 4th value of the distribution. This means the distribution is symmetric about mu naught equal to n into n plus 1 by 4. So, now we formally prove that the distribution of t, that is, the null distribution of t, is symmetric about mu naught. Now, assume theta equal to 0. Then, probability t equal to small t plus mu naught equal to probability summation I from 1 to n I zi equal to t plus mu naught. Now, in this definition, zi are IID Bernoulli half. Since zi and 1 minus zi have the same distribution, we can replace each zi by 1 minus zi in the expression summation I from 1 to n I zi. Then, a rearrangement expresses probability t equal to mu naught plus t as probability t equal to mu naught minus t, and this holds for every t running from 0 up to n into n plus 1 by 2. Thus, the distribution of t is symmetric about mu naught equal to n into n plus 1 by 4. Now, we shall calculate few summary measures of t. First of all, note that the distribution of t is symmetric about mu naught equal to n into n plus 1 by 4. Since for a symmetric distribution, the point of symmetry is the expected value. When expectation exists, we get at once that the expected value of t under the null hypothesis is n into n plus 1 by 4. Now, to find the variance, we use the representation t equal to summation I from 1 to n I zi, where zi are IID Bernoulli half variables. Then, variance of t is nothing but summation I from 1 to n I square variance of zi. This is possible because zi's are IID. Now, variance of zi is 1 by 4 and summation I from 1 to n I square, that is, the sum of the squares of the first n natural numbers is n into n plus 1 into 2n plus 1 divided by 6, and hence finally we get the expression that variance of t equal to n into n plus 1 into 2n plus 1 whole thing divided by 24. Next, we summarize the different forms of Wilcoxon Signed Rank test. Since t has a discrete distribution, tests based on it will be randomized. Assume the alternative theta greater than 0. Then a size alpha test can be expressed as phi naught equal to indicator t greater than t alpha plus a into indicator t equal to t alpha, where a and t alpha are such that the test is of size alpha. Now, for the alternative theta less than 0, we find the size alpha test as phi naught equal to indicator t less than t1 minus alpha plus a indicator t equal to t1 minus alpha, where t1 minus alpha is such that the test is of size alpha. Now, lastly consider theta not equal to 0. Since the distribution of t is symmetric about mu naught equal to n into n plus 1 by 4 under the null hypothesis, a size alpha test can be expressed as phi naught equal to indicator modulus of t minus mu naught greater than t alpha by 2 plus a indicator modulus of t minus mu naught equal to t alpha by 2, where t alpha by 2 is such that the test is of size alpha. Suppose now we want to know the strength of an observed value t obs of capital T in supporting the null hypothesis. The strength is naturally measured by the corresponding p-value. Suppose the alternative is theta greater than 0. Then the one-sided p-value is the probability of t greater than equal to t observed evaluated under the null hypothesis. We accept the null hypothesis if this p-value exceeds alpha. For the alternative, the one-sided p-value is defined as probability t less than equal to t observed under h0. However, for two-sided alternative, that is theta not equal to 0, the two-sided p-value is 2 times the minimum of the above two one-sided p-values. And in such a case, we reject the null hypothesis if this p-value does not exceed alpha. Although we have assumed continuity of f, that is, theoretically, probability xi equal to 0 for every I, but in practice, an observation may be 0. In addition, absolute value of the observations may be tight. Now, presence of 0 and tight observations undermine the validity of the test. Pratt recommended a modification of t in such a situation. Pratt actually suggested to use the zeros and average ranks for the tight observations for the modification of the usual statistic. Now, you can consult the slide for details on this tied arrangement. We have thus discussed Wilcoxon Signed Rank test. We have discussed the distribution free property and few summary measures of the Wilcoxon Signed Rank test. In the next module, we shall provide unbiasedness and large sample normality of the test statistic.